All right. Hey everyone. This is gonna be fun because I literally have 2 talks and way too many slides, so it's gonna be a little bit rush. But I'm putting ideas out there. If you don't understand something, don't feel dumb and just come find me, ask about it. So it's like for small brains, but also brains that are on crack, basically. So I hope you follow me in this journey. So basically, the 2 things I'm gonna speak about is why on-chain games should be roll-up, should use roll-up, what's the point, and what are the benefits. And then something I'm really excited about roll-ups is the possibilities afforded by sequencing to do good things for games. And so I'm going to speak about the design space for decentralized and shared sequencing, which is a little bit technical, but a little bit, fun to talk about if you're a little bit nerdy like me. So I hope you find it exciting. So I had this talk in ETC, which I'm basically going to give you the smooth, speed-up version, like the executive summary of that. Also, I've done this talk like three times this week, so I have that part prayed down, so I can do it fast. So I'm working on a card game called 0x Fable. It's fully on-chain, and it's like Magic the Gathering or Hearthstone. It's under development, and I want to do this game right, so I want to make it decentralized. I want to make it such that everybody can extend it. And for this, it needs to be on-chain, and it needs to be, I think, its own roll-up for a bunch of reasons. This is a gaming track, so I probably guess you know why games should be on-chain, but if you don't, I have a talk at Denver that explains my reasons for that. So here are some challenges that game face. Like game may have a lot of actions, so they need throughput. You probably want to onboard a lot of users, so this user probably don't want to pay 10 cents for each of their transactions, so a transaction should be free. You don't want an NFT drop to just disrupt your gas, so that's gas isolation. You can already see having your own chain ensures gas isolation. You want actually decentralization. You don't want anybody to be able to shut down the game if they press a button. That's the goal. You want cost to be low because you probably still want to make money from your game, so you're running a business. You might have costs, and you have free transactions, so you're not making money on the roll-up, so costs should be really low. As you know, if you ask a user to install MetaMask, and this guy is not in crypto, he's like, okay, I want to play this game, so I have to install this thing, I have to remember these 12 words, write them down, store them under my underwear, and inside my Swiss bank. And then I need to log on to my bank and transfer to Coinbase, and then from Coinbase to Optimism. And it's not gonna work, so you need a way to at least let people try the game for free, and then without doing all these shenanigans. Then there are a few more challenges. These are not super specific to rollup, but like my game, for instance, my card game, you draw a hand of cards, and these cards, the opponent cannot see them. So it's private information. You can't do that in a normal blockchain. You need something like zero-knowledge proofs. I think games should be extensible so that there's a whole software architecture for that. And if your game has some financial aspect, like NFTs maybe, you need trading liquidity so that you can connect the buyers and the sellers. And probably you want to have some kind of people that speculate so that they can supply liquidity on your stuff. So my point is rollups help with most of these for various reasons. And really what they do is that they have low cost and they have good integration and security. So if you don't know why rollups are secure, I don't have time to explain it to you, but just ask me. It's a way to make a chain that inherits the security of another chain, often Ethereum. What's not obvious is that they're cheaper to run than their own chain. You know that there's Cosmos, which is an ecosystem of sovereign chains. Everybody can run their own chain and sort of they all talk to each other. It might not be obvious why running a rollup is cheaper than to run a Cosmos chain, so I'm going to explain that. So there's 2 reasons why the rollup is cheaper. One is the security is taken care by the layer 1 chain, so for instance Ethereum. And so what you need when you run a layer 2 is something called a sequencer. A sequencer is the entity that takes the transaction and makes a block out of it. If the sequencer is evil, 2 bad things can happen. First, if the sequencer just stops, your game is stopped, your rollup stopped, nothing happens. Second thing is a sequencer does not like you. You can just say, haha, I'm not going to put your transaction in the block. That's censorship. But at least the sequencer cannot steal your shit. So that's what we call liveness and persistence, and stealing your stuff. That's security. And so because it's a little bit less crucial, you need less stakers. You need less people to run the sequencers versus the validators. And L2s can do something like restaking and restake. So basically, if you want to pay the validators. If you're a chain, if you're a rollup, you want to pay the sequencers. The problem if you're a chain is that you either have your own token, which means you're printing money. This is great. The problem is like people need to stake your token, so they're exposed to a very volatile crypto something. So they will want to be paid like 50% return every year because of the risk. And you could also print your own token and just spend it, so like that's still money. The other thing is you could use an existing token, so you could use Ethereum. But if you do that, people can use Ethereum to get returns somewhere else, right? They could do staking and earn 6% per year. So you need to beat that rate. If you use something like restaking, it means like people are already earning returns by validating Ethereum. But on top of that, they can also validate your node. And if they cheat there, they'll be slashed also. So basically, they stack the yield and they stack the responsibilities. And because it's additive, you need to pay less of a yield for that. And so that's why rollups are cheaper. The other thing that's annoying if you're a game developer like myself and you want to launch a rollup is you need to recruit all these sequencers, right? If you're a big rollup, if you're Auto Optimism, Arbitrum, it's okay. You just go to, I don't know, Chainlink, you go to Alchemy, you go to Infura, and you say, can you run my node? Can you sign on the website? And they're like, yes, of course, you well know this is a good thing for us. If it's me, they're like, who the fuck are you? Fuck off. And so what I want to do is build a marketplace where everybody that's interested in sequencing can come and say, hey, I'm posting my bond here that is open to be slashed, and I will let you contract my services to sequence your rollup. And then if I'm a rollup, a game, like say that wants to be a rollup, then I come and say, hey, here's my node software, here's how much I will pay you, and then you sort of match these two things, and you cut a lot of the red tape, and so it's easy. Finally, the final opportunity, and this is the bridge to the second part of the talk, is that like decentralized sequencing is when you just don't have a single sequencer, right? So you avoid the censorship and the liveness issue, because if a guy goes offline or if a guy is evil and wants to censor, there's always another guy that can do it after. Shared sequencing is when you have decentralized sequencing, but also you say, well, all these sequencers, they're not just gonna validate one rollup, they're gonna validate many rollups. And then if they do that, what they can actually do is they can do cross-chain transactions that are safe, at least they're as safe as the set of sequencers, and they're fast. They're immediate, in fact. And so this is not very figured out how to do that. There's a big design space where multiple trade-offs, and I want to talk a little bit about these trade-offs today. But it would be amazing, right? Like you have your own chain, you have all the benefits of your own chain. It doesn't have a lot of costs. It's easy to set up, and also you can get instantaneous bridging to other chain. You can get liquidity. You can even split your own game into multiple rollups. I think I have a slide speaking about that later. And so one of the design you will explore is that all your sequencers, that you have a few hundreds of them, one of them is picked to propose, and all the others sign on it. And if you do that, well, you have 200 signatures on your block, and this is less secure than the security of Ethereum, but it's still more secure than just one random dude saying like, hey, this is the block. And so if you're comfortable with a lower level of security, you could use that to do fast bridges, even outside of shared sequencing. And you could also do that for cheap data availability. So data availability is where you put your blocks so that other people can re-execute them. And right now you need to put it on Ethereum, very expensive, on something cheaper like Celestia, EigenDA. But the cheapest thing you can do is not put it anywhere, just on the nodes. And if 200 sequencers say, I have seen this block and I can give it to you, that can be a good enough insurance. Like if you're doing a game especially, and if it's not the economic part, it might be a little bit less secure. Like you say, oh, I'm gonna roll back the last 2 hours of World of Warcraft. It's not gonna crash the financial system. So you might accept the trade-off there. Yeah, so why decentralized sequencing is good for game, I just pretty much explained this. Another thing is that the only way right now to deploy your own rollup is to use something called the OP stack. The OP stack is, as of now, not super secure because there's no fault proof, which is a system that ensures the security. And so in the meantime, like having the signature from the sequencers, that could improve the security of of the OP stack. So if we can implement that fast, that would be great. So shared sequencing, this thing where a bunch of sequencer lets you sequence a bunch of stuff, a bunch of rollups. What can you do with that? You can do game-style sharding. So if your game is so big that it doesn't even fit on a single rollup, you have so many transactions that it doesn't fit, well, why not split it in multiple parts? Like if you have a RPG and you have a continent, put multiple continents in your game, in game world, just put a continent on every rollup. Or maybe split by system. Like the financial system is going to be on our rollup, that's going to be a little bit more secure, and the game system, the battle system is going to be on our rollup, and then you just do instant transactions between them. Okay, this is the first part of the talk. This is gonna be tough. Shared sequencing. I'm gonna rush through 6 models of shared sequencing, of decentralized and shared sequencing, and sort of highlight some trade-offs that you can have there, because it's not like so far I painted a rosy picture, like, oh, we can do instantaneous things that are secure, right? It's not that easy, and I'll explain why. So the basic thing you can do is you have a bunch of sequencers, 300 of them. You just pick one every turn to propose, and that's it. You can do one at a time, so like you're number 1, you're number 2, you're number 3, or you can just pick randomly, and after a while the probabilities will even out. This is actually safe, right? The thing is, it's safe in the sense of rollups. So you can't really, a rollup is really safe to bridge from L1 to L2, right? So from our Ethereum to Optimism, really safe, really fast. From Optimism to Ethereum, you have to wait 7 days to see if nobody says, hey, there's a problem there. So it's an easy design, it's easy to extend, to be shared. The problem is like if some guy says, it's your turn to do a block, and it doesn't answer, well, you just missed the block. Too bad. And then there's this thing called MEV, where people just do arbitrage and stuff. And it would be good if we could capture some of this profit for the chain, and this model doesn't do that. And some of the model we'll see later can do that. Okay, this really simply is just this idea that you have 300 sequencers, you want them to sign on the block that's being proposed, at least 2/3, and you can do a bunch of things that are already mentioned, data availability for cheap, low security bridge. The thing is though, because you need everybody to sign on it, it limits the set of the sequencers. So you cannot do 10,000 sequencers, because then the time to just get everybody to know about everybody else's vote would be too long. So there's a trade-off there. But because we're not using this for security, it's kind of fine. Okay, so this is the model. We just take the previous one, right? Just a guy proposes, and we add all the other guys sign on it, right? This is basically it. It's still safe and fast. It's still easily extensible. Now we get all the extra goodies. We get data availability bridging. You can also sort of, once you see the signature, you're like, okay, my thing is in. Like I can have some confidence that this thing is gonna be on the chain. The problem is like if nobody signs, like if there's a network split and 1/3 of the network is there, 1/3 is there, and then 1/3 is like, I don't know, just nuked by China. Like your consensus is broken, and the question is how do you deal with that? Like do you let it go? Do you go into recovery mode where the signatures are no longer needed? So that's something you need to think about. You're still not capturing any MEV. I'm gonna skip that. There's some way to mitigate the problems. That's what I just said, like just go into recovery mode if you don't get signatures. Okay, so now shared sequencing. Simplest model, you take the previous model, and then what you add on top is like, oh, instead of validating one rollup, now you're validating a bunch of rollups, and you're proposing blocks for all of them. And so what you can do now is like, oh, this transaction wants to do something on chain A, and it wants to do something on chain B, and you're gonna put these two things. And if you lie, the other sequencer will be like, hey, you did the thing on chain B, but you didn't do the thing on chain A, and you'll get slashed, and the block will be invalid. So this is super secure, it's super fast. What's the problem? Well, the problem is essentially the red thing there, which is you're essentially one huge rollup that just happens to be made of smaller rollups. And so this doesn't scale at all. But it can still be useful, right? Because each rollup can be configured completely differently. It can have blocks that take different time. It can have different tokens to pay the fees. It can even be implemented completely differently. And it's easy to parallelize because most transactions will not be cross rollups. You just have one server for rollup A, one server for rollup B, and then you have one server to handle like sort of the coordination of them. But still, it's not really scalable. Some idea to make this better is like, okay, we have a big set, and we're really strict about which rollup can be in this set. But maybe I'm making my game rollup, and I really want to share. I really want to do cross-chain transaction with Optimism. So I'm like, hey, I'm looking for guys to sequence my rollup, but only the guys that are sequencing Optimism can be included. And so that's make it a little bit more permissionless, and lets you sometimes do cross-chain transaction. Another model is, and this is decentralized. So we're going back to decentralized instead of shared, but then we'll do that, but shared. Is the MEVA model, and so MEV is this thing where you extract value from the chain from arbitrage and Oracle backruns, and A is for auctions. And so in this model, there's no like sequencer that's being selected to propose the block. Instead, it's like people are bidding. They say, I want to propose the block, and then we'll pay the network 2 ETH, 10 ETH, whatever, 3 cents, to have this right. And yeah, this is pretty simple. It lets you capture the MEV, which is good. And otherwise, it has all the same characteristic as before. The extension to shared sequencing is Thorny. That's the next slide. And yeah, and there's multiple auction models. So either you need to bid in advance, but then you don't really know about the MEV that you will have. Like you don't really know how much money you can make, so you need to bid very little. Or multiple people are bidding, but they're including all their transaction in public. And that's sort of annoying because people have like secret sauce to make money, and they don't like when that's revealed. And then you can take that and make it shared. So now the model is the person that's bidding is not only bidding to put a block on a single rollup, they're bidding to put a block on rollup A, B, C, D, for instance. But it could also be on rollup D and E. Like they can select the set of blocks that they want to bid for. So this is a great model. I like it because sort of the market decides which rollups are going to be connected with cross-chain transactions. Now there's a hard problem with this, which is like these bids can be overlapping, and how do you select which bid is winning? So I gave an example. You got the first auctioneer on the right, the first bidder, is like, okay, I'm going to pay rollup A $2, rollup B $1, rollup C $2. And then the other guy says, I'm going to pay A $2 as well, I'm going to pay B $3, so that's more, I'm going to pay C $1, so that's less. And the question is, which one do you pick? Because you can accept both at the same time. And if you try to think about all the simple solutions, they don't really work. Like in this case, I'm going to pick the one that pays the most in total, but then that's unfair to, so that would be the one on the right, but that's unfair to B, which is paid less, and maybe B is systematically being paid less, and that's a problem. And you can't also like there are a few solutions, and we don't really have time to go into it, but it's also important that it's not manipulatable. So people like sort of make fake bids to manipulate the thing. So I have a strawman solution there, but this is like just a shower idea basically. If that's something that's interesting to you, just talk to me. And we already had the last one, so I think we'll make it in time. Amazing. So far, the model we've had was the model of atomic execution, where I have a transaction that has multiple parts on multiple rollups, and I want everything to succeed. So sort of a classical example is I want to swap like a token on a chain, bridge the swap token, and buy NFT with that. But if I can't buy the NFT, then I don't want to do the swap in the first place. I don't want to pay fees. I don't want to be exposed to volatility. Another model of cross-chain execution is atomic inclusion, where I say I want to do this action on chain A and I want to do this action on chain B, but it's sort of not a causal relationship between the two. And atomic inclusion does not guarantee execution, does not guarantee success. So you say both of these transactions will be included on their chain, that's what I guarantee, but maybe they will fail there. I just guarantee they'll be included at the same time. So that's a lot less powerful. So you can't do bridging, for instance, because bridging is typically, okay, you lock some tokens here, and then you mint them on the other side. And if you just take that and you include them, both of them, and the locking transaction fails, now you've minted token, and they've not been locked on the other side, so you've just printed money. So that's obviously bad. But if you can do that, and there's some ways to use that with escrow models, or for some other examples that are not bridging, it can be useful. If that's good enough for you, then that's really, really easy to operationalize. Because basically you just make a new rollup. You let it sequence all the cross-chain transactions. So you say, okay, this set of transactions needs to be included, this set needs to be included, etc. And then all the other rollups have to follow this single rollup and just obey the rules. They say, okay, this bundle was a transaction for me, so I should include it. And so that's pretty simple, but it's more less powerful. And yeah, okay, we can skip this. I'll skip this. So I'm interested in working on this. I know there's a lot of other companies like working on something similar right now, and I'm trying to talk to them. My interest is building something that's fully open source, everybody can deploy permissionlessly, make it really easy on the small guy, essentially, because some of the sequencing work is really for the big rollups. I want it to be like, hey, I'm just two guys in a bedroom, we're working a game, we want to do our own rollup. It shouldn't require even tens of thousands of dollars, just a few hundred should be enough. It should be easy to do, just clone a GitHub repo and just do some comments. And there's a lot of people interested in pursuing that vision. And I'm looking for people to build with me, to use this stuff, to comment on it, to fund it, that kind of stuff. So yeah, if you have any kind of interest or any kind of question, if you did not understand anything but you're interested, just talk to me. And yeah, that's about it. Thank you.
You mentioned restaking.
Yeah.
As a way to secure the decentralized sequencers, and then do they apply to all of these models? How do you see them overlapping with the different ways of doing it, different kinds of designs that you showed?
Yeah. So in general, there's two roles to staking. One is Sybil resistance. So if you're going to select in a set like round robin or randomly, you need staking to make sure that I don't come in and like be, hey, I'm 10,000 sequencers. The other role is to prevent misbehavior or discourage. I think in a lot of cases, there's not a lot of safety thing that you really need slashing for, but it's good to desensitize like annoying behavior, like, oh, I'm not answering, and so, encourage liveness, discourage censorship resistance and things like that.
So does it apply to all of the models, or?
I think it mostly applies to all the models. Like you probably don't need it in the auction model, as long as you ensure that the auctioneer always pay their bid, because it might be that they say like they win the bid, but then they don't post the block,
Right.
or they do something invalid. So you want to make sure that in any case they paid what they say they would pay. Yeah.
Got it. Thank you.
Thank you.
Thank you so much for. I wanted to ask. So, I thought like one of the important priority of like shared sequencers is that the, not to be like a bottleneck. They skip the execution part. It just be like the mechanism for ordering. But like when we start talking about like MEV, especially like cross-chain MEV, like does it mean that like shared sequencers need to be like protocol aware and actually like execute transactions to understand like where is the MEV?
Yeah, I don't think any design is really gonna ever be you don't execute. I think you always execute. And the reason for that, even if you design something where you don't theoretically execute, there's gonna be the proposer builder separation, where the proposer is the person that's in the protocol and has the right to propose, and the builder is the person that's actually gonna supply the transaction. There's gonna have a off-chain deal, if you want, with the proposer to do that, so that you can extract indeed the MEV. I guess it could be possible if you don't have any MEV, which for games it's very, very possible that you don't have any MEV, right? So that would be possible.
I see. Okay, thanks. I was just like wondering if like, isn't like it's like another like bottleneck that we like trying to avoid, like going from like layer 1 to layer 2 is like another like.
Yeah, that's a big problem. That's why these things don't scale. And the shared one, for atomic execution, you really want execution. Unless you're doing the last model of atomic inclusion, there you can literally just do sequencing, like you said, without execution. Yeah. All good? All right, thank you very much.